Okay, so it's our great pleasure to have Qing Zhang from University of California, Santa Barbara today. She received her PhD from Texas A&M University and is currently a visiting assistant professor at the University of California, Santa Barbara. Her primary research focuses on tensor category with an emphasis on the classification and construction of modular and supermodular categories. Please, you can start.
Okay, thank you. Thank you to the organizer for this chance to talk at this BIMSA-Tsinghua quantum symmetry seminar. Last time when I visited BIMSA was 2023, December, I think. Yeah, it was a very great trip, and I was pretty jealous about your dining hall. Here, usually I only eat like a Panda Express or some burger for my lunch. But okay, let me just start. I will talk about a project I worked with Zhiqiang Yu last year on realizing modular data from centers of new group categories. So in this project, we looked at some classification result of modular data from a paper by Xiaogang Wen, Richard Ying, and Eric Rao in 2023, and they conjectured that certain modular data can be realized from the condensation of a center of a new group category. So we look at that conjecture, we confirmed it. Okay, so let me. Okay, good. Okay, so let me briefly talk about the motivation for this project. So in this talk, I will assume the categories are all semi-simple and over complex number field. So we consider a modular category over C, and we consider the modular data associated with this modular category C. It is well known that the modular data gives a projective representation of the modular group SL2Z. So there's a lot important result associated to this representation of SL2Z for modular categories, which I will talk about them in detail later. Sorry, just get confused with my mouse. Okay, good. Okay, so in 2023, in Rowell, Wang, and Wen, they introduced a computational process of classifying modular categories through the modular data. So they start from reconstruction of modular data from irreducible SL2Z representations, SL2Z mod N representations, which we will talk about in detail later. And they classify modular data up to rank 6 in this 2022 paper. And later, the rank classification for modular data result was extended to rank 11 by in Rowell and Wen in 2023. So in their paper, they have the list of modular data up to rank 11 with only a few exceptions that they conjecture or they don't, they list as a conjecture how they can be realized by modular tensor categories. So in this project, Zhiqiang and we have this goal of realize some certain modular data constructed in this paper. And the method we use is to compute the Drinfeld centers of near group categories. First, we show the existence of such near group category using Izumi's polynomial equations. And then we constructed the Drinfeld centers also by solving Izumi's equations. And then we identify some Tarnakian subcategory from the center, and we do condensation. So one motivation for us is which you will see the modular data in detail, which is rank 10 one. The reason that we are specifically interested in this modular data because it's a realization not from quantum group categories or not from twisted quantum double. In the literature, this type of categories are often referred as exotic modular categories. Okay, so yeah. So now you can probably guess that this paper itself is quite computational. So probably it's not worth like a 45 minutes talk. So mainly I will focus on review some part of the history and explain how this project fits into like as a small component of a big project of the low rank classification of modular tensor categories. Okay. So the outline of this talk, I divide them into 3 parts. So the first part, I will talk about classification of modular category via SL2Z representations. And then I talk about near group fusion categories and their Drinfeld centers. And finally, after the setup is complete, I will talk about how we realize this modular data from the condensation of the center of new group categories. Okay. So let's start from part 1. So I talk about SL2Z representation associated with modular categories. Okay. So I checked the history of this seminar. I think the audience might be comfortable if I assume they already know tensor categories. So I'll start from let's see the ribbon fusion category. So in the ribbon fusion category, we can use a graphical calculus or ribbon graph. So I'll take the following convention for defining S matrix. In the literature, there are 2 ways, and I'll take this way. So S matrix is the trace of the following double braiding. Here I take X dual braided with Y. Okay, so another one, you don't take the dual. Okay, so from the definition, we know that the first row S is symmetric, so the first row or column and the first row and column gives a dimension of the simple object. So here I use a bold 1 to represent the tensor unit. So that's the S matrix for a ribbon fusion category. So for any simple object in the ribbon fusion category, you can take the twist, and it will be a scalar multiplied with the identity on this simple object X, and we denote this scalar by theta. Okay, so then the T matrix is a diagonal matrix. Consists on the diagonal entries. It consists of this ribbon twist of the simple object. Okay. So there are a few ways to define, equivalent ways to define a modular category. So here, if you already have the S matrix, we say the ribbon fusion category is modular if the S matrix is non-degenerate. Okay, so the pair of S and T is called a modular data of this modular tensor category. So it's well known that the modular data do not uniquely determine the modular category, but still modular data are important invariant to study in the structure of modular tensor category and the classification of them. So here are a list of some well-known examples of modular categories. So they can be pointed, which means that the dimension of each simple object is 1, equivalent definition for pointed. So they can be characterized by an abelian group. For modularity is interpreted as a non-degenerate quadratic form. And more generally, it could be degenerate, but that's not corresponds to modular categories. And Another resource, well-known resource, is from the quantum groups. So you take a simple Lie algebra, consider the quantum group UQG, and at certain root of unity, you get a Raven category, but it's not semi-simple. So you go through this process. Usually, it's called a semi-simplification or purification, and you get a modular tensor category. So this will later I will refer these categories, modular category constructed this way as a quantum group modular categories. So they can also be obtained from twisted quantum double. So if you have a finite group G with a 3 cocycle on G, you take the representation category, you get a modular category. So if you have rep DG, they correspond to, categorically, they correspond to the Drinfeld center of rep G. In general, if you have a spherical fusion category, then the Drinfeld center is modular. So Drinfeld center construction, so the object in Drinfeld center are pairs. Well, Z is an object and this gamma is a half braiding, and these satisfy some convenient construction such that it's a category. Okay, so these are well-known examples. So the modular data we consider this will be in this project will be a Drinfeld center of certain spherical fusion categories. Okay. So now let's move to this SL2Z representation coming from the modular data of a modular category. So let's consider a modular category with this anomalized modular data SNT. And the modular data satisfy the following constraints. So S to the 4 is global dimension square times the identity matrix. And here, this dimension C is a global dimension, so you can obtain it by taking the sum of the dimension square of a simple object. And ST cubed is a Gauss sum of the category times S square. So here, the Gauss sum is defined in the following way. So it generates the notion of the classical Gauss sum, which both are Gauss sum and global dimension are also important invariants for modular categories. Okay. So recall that the SL2Z group is generated by the following, can be generated by the following two matrices, where S is off diagonal and T is this upper triangular. And the defining relation is the following. S to the 4 is the identity, and ST cubed is S squared. So by comparing the relation, we know that if you assign the generators of SL2Z in the following way by mapping small s to S and small t to T, this defines a projective representation of SL2Z. Okay. So an important property of this projective representation rho bar is this congruence kernel property, which I will talk about in this slide. So a subgroup of SL2Z is called a congruent subgroup if it contains some gamma n. Here, gamma n is referred as the principal congruent subgroup. So it's a set that containing all the elements in SL2Z such that A is congruent to identity matrix modular n. So for all n greater than 1, we know that this principal congruent subgroup is in fact the kernel of the natural reduction map from SL2Z to SL2Z mod n. So as a consequence, so if you have some subgroup if you have subgroup containing some gamma n, then if you take the quotient, it factors through some finite group SL to the mod n. Okay, so consider the previously described projective SL to Z representation associated with this modular data. It was conjectured in later 1990s by Koster and Gannon that this projective representation has a kernel, a congruent subgroup of SL to Z. So as an important consequence that the image of this projective representation factors through some finite group. Okay, so maybe let me give a little bit more history about the progress about proving this conjecture. So in the early 2000, Bonte has studied this conjecture with certain restriction in the setting of conformal field theory. And he put this conjecture with a certain restriction inside of this context. And later by Xu, he put this conjecture in the setting of local conformal nets, modular representation from constructed from them. And later, Sommerhauser and Zhu, they introduced this new approach by considering this higher Frobenius-Schur indicator for half algebras. So they proved this conjecture in the setting of for the Drinfeld double of a semi-simple half algebra, and this approach about using high Frobenius-Schur indicator was later generalized by Yin and Schoenberg in the setting of linear pivotal category, and they used this to prove this result for modular tensor category. So now it's widely known that if you have the order of the T matrix is n, then the projective representation of this modular group factors through a finite group SL to Z mod n. Well, here n is the order of T matrix. So this projective representation can be linearized in the following way. So if you normalize S and T in the following way. So we'll normalize S by dividing the square root of the dimension and T by a number gamma, where gamma is any third root of this multiplicative central charge, which is defined in the following way. Okay, so then this will give a linear representation, and it was proved by Donglin and Yin. If n is the order of this normalized T lowercase n, then this linear representation also has a congruence kernel property. Okay, so as a consequence, the image factors through a finite group. So I cannot spend a lot of time on these slides, but it's a very important result to do further classification of modular tensor category. So having this result in mind, we want to ask the following question. So can we classify modular data from finite dimensional representation of SL to Z? Okay, so from the previous slides, we know that the image factors through the finite group. And by the Chinese remainder theorem, we know that you can break up this SL to Z mod n by the prime powers in the factorization of n. So in fact, for each component here, by Knobs and Wolfart, kind of long time ago, the irreducible representation of SL to Z mod prime powers are classified using the subrepresentation of Weil representation. And recently it was proved by Yin and Elon Wang at BIMSA and Wilson that every finite dimensional congruence representation of SL2Z is symmetrizable, which means that you can find a basis such that the representation is a symmetric. So this result can be used in the low rank, or maybe more generally in the classification of modular categories. Okay. So here I will only focus on the low rank classification of modular tensor categories. So in the literature, of course, there are other ways of classifying modular categories by specifying certain invariants. For example, a classification by the dimension or FP dimension, and I guess Elon has a paper on Frobenius exponent and by the weight group. So in this talk, I mainly focus on this low rank classification. So firstly, there's a famous result by Bluield in Rowell 1. States that there are finitely many modular categories of a given rank. So here rank just means the number of the simple objects in your category. Okay. So it was for the rank less than or equal to 4. This was done by Rowell, Stone, and Wang in 2009. So you can see that this paper was before the congruence property were proved. So in this paper, they used another approach. They didn't use a representation of SL to Z, so they used other approach like a Gawa group coming from looking at the S matrix. So then so it was before the SL2Z representation was used widely in this classification. And later, by Bluield in Rowell and Wang, this low rank classification was extended to rank 5. And as I already mentioned that in 2022, they used this computational process to classify modular data through the reconstruction of irreducible representations. And the classification up to modular data is complete for rank up to 6 in this paper. And it was further extended in 2023 up to rank 11, and also for integral up to rank 12. And by Paco and his collaborator, so they have classification of integral modular category, modular data up to rank 13. So maybe before go to the so maybe I'll talk briefly about how this process works. So suppose this computational method works. So suppose you fix a rank, say R, and first you construct all the irreducible prime power level representation of SL2Z of dimension less than or equal to R. And of course, you specify the image of S is symmetric and T is diagonal. And then you construct all finite level representation rho of dimension R as direct sum and tensor product from step 1. And then you construct a candidate modular data, satisfy certain restrictions. And step 4, you apply all the known all the known constraints on modular data to eliminate the invalid ST pairs. And finally, for the remaining modular data, you look for realization of modular categories. So roughly, that's a step introduced in this paper to do low rank classification. So maybe I take one more slide to explain how step 4 works. So this is So we collect some like necessary condition for a pair of matrix to be modular data. So suppose you have S and T. So here, so far we don't add much restriction on S and T. So suppose you have SLT of size L, and you define the following numbers. So you can see that what they are corresponding to. And some necessary condition for this pair of matrix to be modular data of rank R. For example, you have T diagonal and you have order of T is finite and they satisfy these modular relations. And the next one is the number 3 is the famous Verlinder formula. So you need to make sure that if you compute some values using this formula, you need to have non-negative integers. And the next one is essentially you can treat it as a definition for the S matrix, which is also referred as a balancing equation. And other restrictions includes the Frobenius indicator and how the field extension of S fits into T and coefficient. So they are in the more recent paper, they include more, but this one I took from the rank 5 classification, which they refer it as an admissible modular data. So you can see that it's kind of like a lot ways you can roll out some modular some SNT pairs. Okay. Now let me turn to this small like component we did for this low rank classification. So we looked at a rank 10 modular data constructed in Rowell 1. And there's a rank 10 modular data constructed, and it was conjectured in the paper that it can be obtained from the condensation of the center of a near group. But back then when they wrote the paper, it's not clear, or in the literature also not clear if such near group exists. So you need to first show that such near group category exists, and then you look at the whole process. Okay. So here's what modular data explicitly constructed. So maybe let's pause here to make some observation. So you can see that this category is not self-dual by looking at this fourth column and the fifth column, and if you compare the twist, you know that this first column and fifth column of simple object, they're dual to each other, and the next pair is 6 and 7. Okay, so this chi sub n m is this number listed here, and s is an imaginary number. Okay. So in particular, you can see that this category is non-pointed. By non-pointed, I mean that the pointed subcategory of this category is a trivial one. Okay, so as I mentioned earlier, so we showed the existence of such near group category, and I will explain what is this notation exactly means, and we figure out the realization of this modular data. So after this work was done, we realized there's an alternative realization, which is through the center. So this modular data is in fact itself is a center, and it's a center of a rank 4 a new unitary fusion category. So this rank 4 fusion category should be well known for people who study the classification of fusion categories. Okay, so which I will show the fusion role later. Okay, so that's the first big part. Next part, I will review some necessary concept for us to talk about this near group fusion category and their centers. So maybe before talking about what does it mean for a near group fusion category, maybe let me spend one slide talking about what do we mean by a group fusion category. So it's in fact pointed modular tensor categories. Okay, so you will see why we call it a group category in this context. So a pre-metric group is a pair. They can so they are special type of they can be constructed from a special type of pre-metric group. So a pre-metric group is a pair where you have an abelian group and a quadratic form. So quadratic form just means that you have a function from G to complex normal field satisfy the following condition. Particularly Q of G inverse is the same as Q of G, and the associated symmetric function, which is a bicharacter. Okay, so in the literature, it's also referred as a symmetric pairing. Okay, so this pre-metric group is called a metric group is Q if Q is non-degenerate. You already see that these are precisely pointed modular categories. Okay, so that's what we mean by a group category. So the modular data for pointed modular categories are very easy to write down. So the S matrix is obtained by this symmetric pairing of this bicharacter, and the twist are just the values of this quadratic form on each group element, and the fusion rows behaves just like the group multiplication. Okay, so pointed modular categories are relatively simple modular category to study. Their centers are well known, and it's relatively easy to work with type of modular categories. So one may ask, what about the next level of complexity? So which will naturally we'll think about this so-called near group categories. So a near group categories is a fusion category in which all but one of the simple objects are invertible. So you include one actual simple object that outside from the pointed subgroup. Okay, so simple objects will denote them as objects coming from the group and actual simple object row. And it's not hard we're using the restriction of being a fusion category. It's not hard to work out how the fusion row should be. So here I didn't list how the product of a group element, but they just behave like you multiply groups. Okay, so group elements. So the fusion rows of G times rho is rho times G, which is rho is self for all G in G. And rho tensor rho itself, the outcome is an integer multiple of rho and a sum of all the group element. Okay. So the dimension is, if you take the dimension on both sides of this equation, it's not hard to tell that the dimension of rho should be this number by solving a quadratic equation. And so notice that to describe the fusion row of such near group category, it suffices to specify what is the underlying group and what is multiplicity here. So that's why we use this notation that a near group category with above fusion row is denoted by G plus n prime. Okay. So there are some well-known examples that fit into this context. For example, Tambara-Yamagami category, which is has a fusion row where you take n prime to be 0. So these are of type G plus 0 and are completely classified in this paper by Tambara-Yamagami. And the Fibonacci category if you check the fusion rule, tau tensor tau is 1 plus tau, so it's of type Z1 plus 1. And rep S3, so if you take the two-dimensional representation, you have the tensor outcome like this. So particularly it's of type Z plus 1, a near group category. Okay. So there are some classification results for near group categories. Basically specify what this n prime value would be. So given a new by Evans and Ganner's result, so given a near group category of type G plus n prime, so the only possible values for n primes are 0, n minus 1, which we saw the example of rep S3, and n prime is multiple of n. So here, this n is the group order. So so in this paper, we focus on you can see from the notation, we focus on a special type where n prime coincides with n. So these categories can be completely characterized by Izumi's polynomial equations. So, well, in general, if you want to construct a fusion category, you need to solve the pentagon equation. But Izumi's result suggests that for this type of near group category G plus n, you can use the following term to describe the full category. So it's characterized by the following element. You have the group G, and you have ABC, which will be specified later, and this bicharacter. And they satisfy the following constraints. So here D is just a dimension of the non-invertible object. Okay. So the polynomial equation is, there are few, quite long, but let me try to explain as much as I could. So you can see that this A as a function is in fact a quadratic form, and it's by the restriction of this bicharacter being non-degenerate, we know that A has to be a non-degenerate quadratic form. So these are classified once you specify some abelian groups. And if you look at this equation, so notice that this is for the pointed modular category corresponds to this quadratic form. This is a Gauss sum, and this is a normalized factor. So if you divide n squared to the other side, you get the central charge of the pointed part of like associated pointed modular tensor category. So for experts who study the representation of SL to Z, we know that this C is a third root of the multiplicative central. C is a reciprocal of the third root of multiplicative central charge. So C serves as a like a normalization for this representation. So the function for B is kind of not very clear. So in general, this is a so if you solve this equation, that's the hardest part to solve for this function B, but they satisfy certain constraints related to the rest of this component here. Okay. So when two such near group categories are equivalent, so in fact, if you have some automorphism of G, some map, such that they satisfy this precise satisfy the following condition, you can show that it's enough to tell that the underlying fusion category are equivalent. So you could, at other nodes, you could have different solutions, but potentially they are equal. They give you equivalent fusion categories. So some result about the existence. So in Evans again, they solve these polynomial equations, and they show some existence of the solution. So for cyclic group of order less than or equal to 13, they show a solution exists, and they show some other non-cyclic group existence. And they show no solution for this elementary abelian 2 group. And in fact, by a paper by Andrew, So he studied this categorification of a new group fusion ring, and he proved that it's categorifiable if and only if for abelian 2 group, if only if you have either 1 copy or 2 copy of Z2. And the solution existence were extended by Gannon's master student Prudinsky in his master thesis. So he showed that existence for the following cyclic group. So 29 is missing potentially due to some like mathematical error. So conjecturally, they should also exist. And in general, conjecturally for cyclic group G, this new group of type G plus N always exists. So recall that if you have a fusion, spherical fusion category, you take the center, you get a modular tensor category. So once you have the data for a new group fusion category, so there's a formula by to solve for modular data for the Drinfeld center. So this formula was provided by given by Izumi using the tube algebra construction. So so to obtain the modular data, you need to further solve some equations, polynomial equations for triples. So here, psi is some function from G to root of G to usually a root of unity, but a complex number of length 1, and tau is a group element, and omega is some root of unity, and they satisfy the following polynomial equations. So the equations in general is very hard to solve, so you need to run like a grammar basis to solve it. But once that is done, you can write down the modular data. Izumi also proved that there are n times n plus 3 divided by 2 triples solution for this polynomial equation. And then the corresponding center has rank n times n plus 3 with the following up to dimension there are 4 subsets. And the first one corresponds to the pointed one. So the dimension of the first class is of dimension 1. And second class also indexed by the group element, but the dimension is d plus 1. And the third class indexed by pair of group elements. There are n times n minus 1 divided by 2 of them, and the dimension is d plus 2. And finally, the hard to solve one are the first class of them. So they correspond to the solution to the triples, and the dimension is the d. So recall that this d is the dimension for the non-invertible object in your original near group category. So after you solve the triples, and you can write down the modular data, and explicitly you can write down this way. So by looking at the construction of the modular data, we know that the first class corresponds to the pointed subcategory. So if you look at, for example, here, it corresponds to the pointed subcategory of the center. So even though it's hard to solve the triples, but you can easily quickly write down, once you know the underlying new group category, you can quickly write down the pointed part for such for the center. And notice that by the expression listed here, so almost all the component, all the entries are now hard to write down except the following one. So which is the lower right corner of this block matrix, which is here. So you need to really use a solution for the triples to construct this part. But the rest of the part are relatively easy. Okay. Okay. So there's an interesting conjecture regarding the modular data for the centers. So it was first conjectured about how the modular data would look can be easily obtained, relatively easily obtained by looking at two metric groups, satisfy the following condition. So the group order has to be differed by 4, and the multiplicative central charge are negative to each other if the group is odd. For the group, then the lower right corner can be relatively kind of long formula still, but relatively easy to write it down. But it's only a conjecture for now, and it's verified for n less than or equal to 13. And later, this conjecture was generalized further by Grossman and Izumi, and by Berdinsky in his master thesis. And one interesting fact by looking at this conjectural modular data is that the multiplicative central charge, you can also obtain multiplicative central charge not equals to 1 modular data from this conjecture. So for centers, the multiplicative central charge will always be 1. So you can construct a modular data that potentially not related to, that's not actually centers. And there's a paper by Bonus and Rowe and Wang can actually realize this conjecture modular data by zesting and gauging. So towards the end of part 2, I talk about this. We show that the existence of such new group category. So if you take this non-degenerate symmetrical bicactor on Z4 cross Z4 defined like this. This was actually originally conjectured in the 2023 paper. And then we go and solve Izumi's polynomial equation. And I try to write down the functions in a relatively nice way. This is as much as I could do. So notice that in particular the solution for this B function, it don't sit in the cyclotomic field. So it's kind of hard to tell what exactly is happening by looking at the solutions. So we found a solution associated to this particular non-degenerate symmetric bicactor, and so this is one solution. We actually found 4 solutions, but up to equivalence of fusion categories, there's a unique one corresponds to this specific bicactor. And we construct the modular data after having this existence. Basically, we go solve the triples listed earlier. Is kind of unpleasant to solve, but we were able to find the right amount of solutions, and then we can write down the center, the modular data of the center, which is a rank 304 modular category with the following simple object. So here I just listed the dimension expected, and just as a comparison with this the modular data we need to realize, you can see some patterns. So for example, this dimension chi 89 survive after condensation, and this 4 times chi 5 2 also survive. And notice that you have this dimension chi 25, and originally you don't have this dimension in the category, so you can kind of guess that what happened under the condensation functor, which we will talk about later. So they split after condensation. So also it's not hard to write down the pointed subcategory of this category. So here you can, so the pointed part can be written down here for the modular data. Notice that the twist is 1 if G1 and G2 have the same parity. So you can immediately tell that this center has a Tarnakian subcategory of rep G. So G is a Z2 cross Z4. So So for the last part of this talk, I'll talk about you use this RepG to do condensation of the center. So we consider the condensation of the center by this Tanakian subcategory. So I will talk about the part 3, which is the last part. We realize it's modular data from the centers using condensation. So as a tool, I will just briefly talk about how to briefly review how we use this condensation in our setting. So you can see different names, but they are kind of related to the same concept of condensation. So for example, you can see by in a module, you can see the name modularization or modules over an algebra object or GD acclimatization. We only consider condensation for modular tensor category. So if you have a modular category and you have a RepG as a Tanakian subcategory, and you can consider the GD acclimatization, which is a braided G-crossed fusion category. And the trivial component is a modular category. And the dimension, you can write it down here. It's just taking a ratio divided by G square order. And this by Boson condensation, it's just this trivial component, which is again a modular category. And for computational approach, we actually used in this paper, we use another way, alternative way to think about it. So you consider an algebra object in RepG, and you consider the category of A modules, and then the subcategory of local module, which is coincide with boson condensation and can also be characterized as the GD acclimatization of the centralizer of RepG inside of C. Okay, so recall that for us, the RepG is, G is Z2 cross Z4. Okay. So by Muger's result, so since we already, we successfully got the modular data for the center, so we can, by Muger's result I think it's usually called the central, I forgot usually called, but Muger's theorem that by looking at the entries of S, you can obtain the centralizer of RepG, and particularly has rank 44. And by further checking how these algebra objects act on this centralizer, we obtained the fusion category of rank 10 with the expected simple objects. Here you can see that some of the dimensions split into 2. And the corresponding T matrix works as what we expected. And so that's only at the level of the dimension and the twist. The twists are relatively easy to obtain. So to completely determine the S matrix, by looking at the twist, we know the level of the SL to Z representation. So you just need to look at the level SL to Z representation at level 4 and 5, and you rule out all the other possibilities, and we end up with this unique rank 10 modular data. So this theorem is basically summarize what we went through from the previous slide. So we found a realization for this rank 10 modular data. So in fact, after this was done, so I talked about this in our group seminar at UCSB, and Zheng mentioned that potentially this rank 10 modular data also corresponds to a center. So, it could be some fusion category people already know. So we looked at the literature, and we realized it's in fact so here's some proposition we proved as a corollary by some of the result from Austrian and other people, but particularly we know that the underlying rank 4 fusion category is there are probably many references you can see that this rank 4 fusion category is a self-dual fusion category. For example, maybe earlier reference, you can already see that people constructed this fusion category. And we showed that the rank 10 modular data can be also realized by the center of this category. But we didn't go through the tube algebra construction to explicitly computing the modular data starting from A. But we did just use some existed classification to rule out other possibilities. So we conclude that this is also the center. And I think I don't have much time left. Just another example we did, which is for me, I will think it's less interesting because underlying modular data is related to a quantum group category, not as exotic as the previous one. So if you think about near group category of type Z2 plus 8, then you do a Z2, you can find a Tannakian subcategory of rep Z2. And after the condensation, you can factor a pointed subcategory, modular pointed subcategory out, and you get a rank 9 modular category, which has the same modular data as a G2 level 4. And it turns out there are many examples you can construct from looking at the near group centers. In general, the center is huge. It's of size n times n plus 3. But oftentimes you can either do condensation by identify some symmetry in this center, or you can factorize some pointed subcategory out. So here is some. It's not complete, but these are some known examples that fits into this big picture. So here we did this one, and there are some other paper I did, and some other paper that we know that it can be constructed from the centers. Okay, so I think I managed to finish the talk within an hour, and thank you.
Thank you. It's time for the question.
Should I stop share screen, or I can wait? But
maybe someone will ask you to.
Okay.
Yes. So,
Resume. Okay.
Is there any way to calculate the F symbols of a near group category?
I'm sorry. Can you repeat? Sorry.
Is there any way to calculate the F symbols of a near group category?
I think it's essentially characterized in so the Izumi's let me find it out. So it's essentially inside of Izumi's polynomial equation. So this by solving this equation, I didn't carefully check his original paper, but this you can. So after you have the solution for this near group category, you can potentially recover the F symbol from it. Because people told me that essentially this solution to these polynomial equations corresponds to the pentagon, solution to the pentagon equation. But I don't know a quick way to write down the F symbols for a given near group category.
Thank you.
Thanks. Sorry, but maybe Tambara Yamagami, if that counts as maybe an example too. So these are classified. Yeah.
From your, may I have a question?
Sure.
Thank you for the very nice talk. So, in your talk, I think there is a slide relating quantum group G2 and uh, the category come from the center of some near group, right?
Yes, that's towards the end, right?
Mm-hmm. So this indicates that uh, the center of the near group may be related to the quantum group in some way.
I think so. Yes, by maybe I need to think carefully. Maybe by this result, you can think about it's potentially related to some quantum group, but I'm not too sure about it. Yeah, just my.
Yes. I mean, probably there is a way to construct more near groups using the quantum groups because I think there's a conjecture saying that all the modular tensor categories come from quantum groups in some way.
Um,
I,
um,
On the width class.
to the up to weight class, there's a conjecture, but I don't know. There's a conjecture,
Width class.
but yeah, there's a conjecture about up to weight class, but I think there are still some people believe they are exotic modular data. So yeah.
I have several questions. So let me say them one by one. What about find a model like that for extended group, the center of extended group category?
The modular data for, sorry?
The center of extended group fusion category.
Extended Hager.
I'm not sure. I think probably Izumi has some. I'm just not very sure. I think probably can check Izumi's some results through tube algebra construction. But yeah, I don't know about the answer for this question. Yeah, sorry.
So the next question. So in one of your slides at the end, you said that this kind of construction, the condensation of center of near group is always the center of a fusion category. So this is really
You
what
mean this result?
Yeah. So it's always so it's the width class is always trivial in this according to this proposition.
Yes. So but we need to add the assumption that it's abelian.
Ah, okay.
Mm.
And the next question is, so is there a constraint in this process that would prevent to be able to make the integral modular fusion category by this way? At least,
Oh, you think about integral fusion category?
yeah.
Oh,
Modular fusion category. Is there a constraint we prevent to be able to make such integral modular fusion category by this process? At least,
I think. Let me think. I think it will not be. I think for this type, probably it won't be integral because this D is, you can see that the D is some like number at the square root of some other number divided by, yeah. So I think this will prevent this process, after this process, you won't get the integral modular category, because the condensation will change the dimension, but probably not. You will. It's unlikely you will get it. Yeah.
Yeah, because if you look at what's the formula for D, right?
Yeah, except if D itself is an integer. If you choose an integral near your category, maybe. You have more chance.
So D itself, for large n, D itself cannot be an integer, that's your point. Because you have a square root of an integer square plus 4, and if you have a square plus 4, and if this integer is large, then it's
So only for small range.
Yeah, only for small n. You can possibly have some integral.
Yeah, but I think in general you can, but probably for it's unlikely you will get integral ones.
Okay. And the last question is, so in this paper by N. Growell and Wen you mentioned several times, in the introduction they mentioned another open modular data of rank 11. I don't know if you know what I mean. In the introduction of that paper.
I have no idea. Maybe Yilong has. I have no idea how to realize it.
Because I discussed by email by Eric, and he said, some people are working on that. So do you have some news about that? Or do you know who is working on that, or what?
I would guess. No, I don't want to. I don't know. Maybe. I'm not sure, but I'm not working on that. I can tell you that, but I don't know who is working on it. Yeah.
Okay. So that's all for my question. If there is a question.
Yeah, there's a very interesting observation. You can see the people have found G plus N, right? And they have all shown they check it for some cyclic group and they believe it exists for cyclic group, and they also check for some simple group for groups having two cyclic factors, right?
I think it's when you add more. That's what Andrew told me last summer, and that's a guess. But if you have like a more component, say like a few more copies,
will that be true? So, for example, is equal to the zip grid. Will that exist?
I tried to solve, but I couldn't. So far, I couldn't find. Like for example, I tried to solve Z2 cross Z2 cross Z5. I couldn't figure out. That one. I couldn't figure out if there's a solution to it. In general, I think it's not known. Like we only know probably there's a hope.
How hard is the computation with respect to the order of the group?
It's you basically look at a polynomial equation, you run a Gromov basis.
So how long did it run for your computation for Z4, Z4, 16?
Once I've set up the bicactor, it's not hard. It doesn't take me too long to compute these functions A, B, C.
Okay.
But to compute the modular data, when you need to figure out 152 solution for the triples, that took me like I don't know. I don't want to say that. Kind of. So maybe it took me a while, like 1 or 2 months, because I'm not like very good at the computer. And if you use Mathematica, sometimes you run into some like error. So even though there's a solution, you might miss this. So you have to like change something to make sure it works. And you need to look at so for example, basically you kind of try to guess. So for each group element, you insert a tau, and you try to guess what is like a bond as a cyclic, as a cyclotomic, as an element in the cyclotomic field extension, what omega would be. You try to guess the level of the omega, and you try to solve for each special case, and you try to figure out all the, that's a method I use, but I don't know if there's a fancy way to program it. Yeah.
Oh, okay.
Mm.
Okay, thank you. Any other question, online or offline? If no question, let's thank you again.
Thank you.